I am Frank. I am a physicist from Victoria University of Wellington. I'm very pleased to be here to talk about nanomaterials and materials with you.
Cool. And I'm Michelle. I'm from the University of Auckland, and I'm going to start us off with a history of the materials in New Zealand. And what's really fun is being able to give this talk in New Zealand, because we have a really unique history that nowhere else in the world can claim. And so let's start at the beginning. So we are both from the MacDiarmid Institute, named after Alan MacDiarmid, but actually started by the late Sir Paul Callaghan. And we are a materials and nanotechnology research centre, but we don't actually have a centre. We're basically researchers and academics from all over New Zealand who work together on collaborative projects to help create new materials for New Zealand that will hopefully help change the world. And this is what most of us look like. There are a few people missing here, but this is about the size of our research group. Both Frank and I are investigators into different types of nanomaterials. And this is what we tend to do with our days. So we build materials and devices from the atoms up, usually, or we understand how the atoms make materials using all sorts of things. So Frank is a physicist, I'm a materials engineer, and we build and I break stuff to try and make it better. Now here's the thing, when I said to my mum, hey mum, I'm going to go to university and I'm going to study materials science, she assumed I was going to make dresses. So most people's opinions of materials, that's a true story, most people's opinions of materials are this. When you say materials to people, especially when they're females, they tend to think fabric. Fabric is just one type of material. As materials scientists and materials engineers, we don't just use fabric, we use the building blocks of any sort of material. So bricks and wood and metals are all materials that we're really interested in. And you can think of materials over history as ages. So we know we started with the Stone Age, and then we went through to the Bronze Age. And the Bronze Age is really interesting because you see the two bronze pots there. They look very similar, yet one of those came from China and one of those came from Europe over the same period of time. So very different communities and civilizations were discovering the exact same things and how to make them over the same period of time. So bronze was really interesting because they could combine tin and copper. And bronze is great because it melts at a very low temperature, meaning that you could just do it over an open fire. So you didn't need anything complicated to make bronze. And then over the next period of time, we as humans developed furnaces. Now furnaces meant that we could heat things up to much, much higher temperatures. Bronze is great for holding your food in, but it's very soft as a metal. Iron, however, is very hard and could be very sharp, so you could mold it into weapons, for example. And the only way we could do that was the ability of making furnaces that made the temperature high enough. So it took us a long time to be able to do that. And the question is, did the Iron Age ever stop? And if so, what age are we in now? So what's fascinating about the Bronze Age when you learn about it in history is when does it start and when does it finish? And that's always going to be dependent on where you're learning it from. So I was educated in Europe and we had very definite times based on when the Europeans had our Bronze Age. But that was all based on transport mechanisms and communities. And so the Bronze Age actually shifted for different communities depending on when it was discovered, how quickly things could be transported to other areas, and how quickly these ideas were told amongst different civilizations. Now the question is, what about little old New Zealand? Did we follow the same map? Because we were quite isolated, and were we involved in the same conversations as the rest of Europe and China? Here we are. And if you follow that Bronze Age map, you'll see that actually for many things we had a very different timeline because we were quite isolated. And so if we look at the materials history of the Pacific and what happened here in New Zealand, we followed some of the similar ages, but we have something very unique. And we have our own Stone Age. But our Stone Age is actually very modern. And we're going to call this a high-tech Stone Age. And this is our economy based here in New Zealand, based on things like obsidian and punamu and the stones that we know very well today. Top of my slides cut off. Anyway, what's unique about New Zealand is we have this amazing natural resource. Our geography is incredible, we're volcanic as an island, and that gives us amazing rocks that have incredible properties that we were able to not only mill up and create quarries from, but also to sell and trade and do different things with. And so what is really unique about some of our materials, let's say obsidian. So obsidian is a volcanic rock. It's very unique because it's almost glass-like. And so it makes it very, very sharp, meaning it's good to use as an axe or as a weapon. You can fracture it, and it fractures along a perfect crack line, making it very easy to use as a cutting tool. Now in Te Hoa, Mare Island, that's probably one of the best resources of getting this type of rock around New Zealand. And what we were able to do back in the 1350 AD, is not only pick up this rock, but transfer it over the whole of New Zealand very, very quickly, so that all of the everybody around here could start using that as a cutting tool. So they've been found in archaeological sites in 1350 AD, and only 40 to 50 years later, we were able to find that it didn't just leave the island, go to the mainland, but actually it was found in the Chatham Islands and Antarctic Islands. And so what we're really good at doing in New Zealand is not just finding the resource, then turning it into something useful, in this case a cutting tool, but then exchanging it and distributing it and trading it very, very quickly as a trade to areas that are relatively remote. So in only 50 years, they were able to find it, mine it, make it, transport it. And that's something we're really good at doing in New Zealand. What was also interesting, so back in 1350 AD, we didn't go looking for things in easy places. The places where a lot of these original rocks formed are tough places to get to. Not places that we were finding our food, not places where we were settling, places that our Māori ancestors actually were walking over crazy volcanic hills and into quarries. And this is Bluff Harbour, a very remote quarry site that they went to find the best source of material. So you could find some of these rocks in other places, but what they did is spend a lot of time finding the most unique and purest source of some of these materials. And this is, again, the same sort of rock that was used as a cutting tool. And then they would travel huge distances. So we found a manufacturing site back in 1400s, 250 kilometers away this was from Bluff. So they would carry all of this natural rock 250 kilometers away to manufacture it at a place that was more useful, and from there distribute and trade. So the fact this was happening only in 1350 AD, it's a relatively new Stone Age if you look at the history of the eras of materials, but for New Zealand it was a very unique time and how we've used our geography to create materials for function. And so our exchange networks were crucial in being able to trade and monetize and create exchanges for things, and that's something that New Zealand has done incredibly well. So what's unique to us? These are three things that we're going to come back to. New Zealanders and New Zealand research is good at finding quality materials. We then are really good at controlled manufacture, and then we add value and sell it on. That's pretty much what we're good at. And so it's not just what you have. Having a raw material, having a raw rock isn't useful on its own. It's how you convert that to something that is a high value trade. And that is what we are really good at. And we do that now in New Zealand in the metals industry. So we have Tiwā Point and we have New Zealand Steel. Both are very unique in what they do. New Zealand Steel is fascinating because we take our black iron sand, we basically take a magnet to the beach. And if you've never seen this, if you haven't done this, take a magnet to a black sand beach and put it in, and you'll see this incredible array of almost this floral sand that, as the iron sand aligns with the magnetic fields within your magnet. We do this on a very large scale with New Zealand Steel, and we make some of the purest steel in the world with some of the highest value because it's so pure, because it's made from iron sand instead of taking it from rocks. It actually, the Japanese love it, and we charge a huge amount for it because it is so pure. So again, what we're unique at doing is finding the raw material and making it very, very high value. And we make some of the purest steel in the world. And we also make incredible aluminium down at Tiwā Point. So what age are we in now if we're not in the Iron Age? Some people will say, well, we're in the Silicon Age, because I don't know about you, but many of us can't live without our technology. And our computers and our devices are based around silicon chips. And so if we are in the silicon age, what does that look like and where is that going? So we have this thing called Moore's law, and it's a thing we're trying to keep to. And basically that says that the number of transistors on a chip doubles every 2 years. And to date, we are still along that. Now, if you're going to double something every 2 years, you either have to make it much, much bigger every time, but I don't know about you, my phone isn't getting, I wouldn't like a phone that was the size of a plate. Or you have to make it much, much smaller and be able to hold more things. And that's what we've actually been doing. So if you're going to make something much, much smaller and hold more things, the things it holds must be smaller to be able to do that. And so this is where we come in as nanotechnologies. So this is a recent silicon chip. This is what goes inside your computer. This is an Intel chip. And you can see it is the same size as a grain of rice. So that's what we're making right now. Now, if you zoom in really closely onto that little chip, you'll see that the transistors and all the technology that are etched out of silicon there are incredibly small. And so that is how we've been able to keep with Moore's law. We just make features that are much, much smaller. So how small is small? Well, how small can you see? I'm going to ask you all to do an experiment with me now. If you're follically challenged, I'm very sorry, but everybody else, can you just take one of your hairs? You may want to ask your neighbor if you can borrow one. Now, if you can either pluck it, or if you've got it long enough you can see it. Can you see the hair with your eyes? Yes? You can see it, yes? Okay. Now, if you can see it, you might need to go a bit cross-eyed for it. Can you see all the little features on it, or can you just see if it's a hair? Yeah. It's just a hair. Nobody can see the little features that are on there. I can tell you there's beautiful features on your hair. Anybody see that? No. Okay. We are using visible light, so light from up here to see that. That's what we use with our eyes. This is what your hair looks like. And your hair is 100,000 nanometers wide. So you just saw 100,000 nanometers. What you didn't see is probably the detail on your hair, the little cuticles that are on your hair. And I could probably tell looking at those cuticles if you use conditioner or not, because conditioner flattens those cuticles down and makes your hair look nice and shiny. So if you can see 100,000 nanometers, you can see the width of that. As nanotechnologists, we are creating things that are 10 nanometers, 1 nanometer. So we build things that are 100,000 times smaller than the width of your hair. Now that means we can't see it. And so we use visible light to see with our eyes and see things. But visible light has a wavelength of 400 nanometers at its smallest. Meaning that the things that we're making are smaller than the wavelengths of the light that we're using. So we don't use light to see what we see. We use electrons. And so if you bombard electrons at the surface, you can actually measure the response of that. So this is a flea. Using an electron microscope, or a series of them, this is a video created by National Geographic, where you can take a flea, and what you'll see is a flea has ear hair. Yeah. I know. So if you think of us as nanotechnologists, we are building things that sit on the hairs of the ears of a flea. That's the scale that we work at, and that's how tiny it is. Just to let you know, this flea has been artificially colored. They're not really red. It just looks prettier, because electron microscopes only give us grayscale images, and a black and white flea isn't much fun as one that you can see that is red and yellow and ghastly. So this is the scale that we work at. And so we can create structures that look like the ear hair of a flea using lots of different things. Mostly electrons, and electron beams are what we use, or ion beams. And we can create these little whiskers, for example, out of silicon. And this is how the silicon chips in your phones and your computers are getting smaller, because we can put more onto them by making the things that we put onto them smaller. Now, I get asked all the time, oh, this nanotechnology, it's so new, I've never heard of it, it's this new thing. I'm going to tell you it's not very new at all. And if you've ever been to a cathedral and you've seen stained glass, the red in the stained glass is colored by nano gold, and the yellow in stained glass is colored by nano silver. And so different nanoparticles, gold and silver, which are obviously gold and silver in visible light, when you make them small enough, they behave differently and they come off as different lights. So we can see in the cup that is red and green, or in stained glass that is red and yellow, we've used nanoparticles of things that we already know to change the way that we reflect and view the light. And so stained glass is actually nanotechnology from 1500s.
Wonderful, Michelle. Thank you very much.
as you said, Michel, silicon has had a humongous effect on our way of life. And that's basically, there is hardly any part of Michel's life, my life, your life, our world that is not touched by this material called silicon, you know? And what is quite important is this idea of using silicon is our ability to control the size, the structure, in order to control new properties that can be used in today's computer or smartphone. And this ability, in fact, has triggered a lot of attention in the material science community. If you think about what people like Michel or myself or other scientists, we started to think, okay, that's really fantastic. We can make this lovely computer, smartphone, but they are made of silicon. And what about trying to do what we have done with silicon with other materials? Not necessarily natural materials, material we can create, conceive, think about, design, to get new kind of properties. That's what I want to talk about. In fact, what I should say first is, I can summarize what I said by this nice sentence that from professor in the US. And he said, whoever controls the materials, in the sense the material, the size or the structure, will control the science and the technology. Apparently, we didn't control the material. Or not enough. And you know, at the end of the day, we are basically all consumers. So we are interested in an electronic devices, a computer, a smartphone, or something else. So we like technologies. But first of all, we want to control the materials. Okay. What I would like to say now is, okay, you now understand or you have a good idea or concept of what is nanotechnology. Okay, that's the idea to controlling the size of the structure to get new properties. If you're interested in getting more details, okay, if you want to understand a little bit more in details what is nanotechnology, you have to start to think about something at the atomic level. You have to think about the atoms, okay, of the position of the different atoms, the arrangement of this atom within the solid, how they are bound together. That's something very important. And I have to take an example, and probably carbon is one of the best example. What can we do with carbon? We all know about carbon, you know. The most known form of carbon in its pure way is that's a diamond, this lovely jewel called a diamond. Within this material, this diamond, okay, the carbon atoms have or are arranged in a very, very particular or specific way. That leads to something that looks like a three-dimensional structure or object. That is the diamond, your jewel. Okay? Now, if we rearrange these carbon atoms differently, as it is shown on these different layers of carbon atoms, or these arrays of carbon, we get a new materials, a new substance that is called graphite. And in fact, you're familiar with graphite. That's what you have in your pencil every day when you write at school or at home. Okay, but it's a good point here. What I want to point out is that the fact we have still the same kind of atoms. We still have carbon atom. What we have changed, in fact, is that the structure. And by changing the structure, we have a new material. And now what I want to show you is that instead of to change the structure, I can change the size of my material. That's what you do here with what we call graphene. You just take one single individual layer of graphite and you create a new material that is a two-dimensional material called graphene. Okay, so here, same structure, I have a change the size, and I have a new material. And you can think about rolling up this graphene into a tube or a pipe, and you end up by having a nanotube because the size is very small. That's what we are calling that a nanotube. What we have done, that's a nanotube of carbon. And here, as I said, just by playing with atoms, with their size and structure, we have been able to change completely the different materials we have created without changing the nature of the atoms within the material. But if you remember, as I said, whoever controls the size or the structure or the material will control the technology and the science. So what I want to show you now is that's what kind of properties we can get from these different materials. If you take, for example, on the left, still our dear friend carbon, but in its graphite form. In fact, graphite is a very good conductor. It can conduct electricity very, very well, like a metal like copper, a wire of copper or copper of aluminum. On the other hand, if you take diamond, you probably know that diamond in fact is an insulator. It cannot conduct electricity. It doesn't like electrons. And you end up by something that is kind of like a piece of rubber. So you can see same atoms, same type of atoms. We have changed the materials and we get different properties. And that's quite important because at the end of the day, if you want to create a function or you want to create an object for a specific purpose, well, you have to decide what you want. If you want, for example, a conductor or an insulator. And you can extend this. There is something we haven't been talking about so far with Michel, that's mechanical properties. Well, you know that if you have a lovely diamond, diamond is something extremely strong, hard. Well, if you take your pencil or a piece of graphite, you know that's kind of brittle, that's soft. So once again, you have different materials, same atoms, but different mechanical properties. And at the end, what we are interested in, that's what I'm saying as a title on the title of my slides, that we are moving from a structure to a function because we are interested in developing new function, something we might be interested, something insulating, something strong, and so on and so on. So the idea by being developing materials, that's kind of always trying to solve or propose a solution or a function to something. And at this point, one of our colleagues, to Michel and myself, Nicolas Gaston, say, "Oh, Frank, you should talk about Napoleons." And I said, "Oh, cool. You know, we love Napoleons. I am French. But I also understand that in this part of the world, or in the UK, it's not a legend. But anyway, I will stop here." And she said, "You should talk about Napoleon's buttons." And I said, "Ah, yes, she's Kiwi. Now I understand what's the problem." So Napoleon's buttons, that's kind of interesting story. So as you can imagine, that's Napoleon in Russia about 200 years ago. It was victories after victories, obviously. He crossed Europe, he arrived to Moscow. He said, "Oh, that's a nice city, but I'm missing my dear France. I want to go back to France." So he decided to walk back and withdraw with his troops from Moscow to France. But he decided to do that in winter. And winter in Russia, that's pretty cold. Apparently, it went down to minus 30 degrees Celsius. And here is a story. So the story called maybe the greatest wardrobe malfunction of the entire history of many things. It can be seen as war, it can be as clothing, it can be, anyway. What happened that the buttons on the coats, on the clothes of the soldiers were made with a material. This material was a metal, and it was tin. And tin doesn't like cold at all. So basically, the buttons fell apart, completely disintegrated, and the soldier didn't have any more buttons to close their coat and other clothes. And apparently, that's the reason that is mentioned as the reason of the death of nearly 80% of the entire army of Napoleon. So always important to use the right material for the function you're interested in. Okay, I'm moving towards something that is more recent. That's something basically we are dealing with every single day and mostly from an environmental point of view. So far, there is another property of materials I haven't been talking about. That's light. It appears that we have materials that are able to emit light under specific conditions, and these materials are under a very high demand. And in fact, you can understand this by looking at these kind of pictures, which is showing how Earth looks like from space during nighttime. Okay, I used to call that "What do the aliens see?" And one day I went to a school, and one of the little kids said, "Oh, Frank, I think you're wrong. They don't exist." I said, "Oh, okay, it doesn't matter." But anyway, whoever is watching us, this person will say, "Oh my God, these guys are crazy. They use a lot of lighting." In fact, we can see that's basically all the different parts of the world where, in fact, very advanced countries or modern countries or very industrial countries, we are just here. You can say hello to the guy in space. And what you can understand from that is the fact we are using, in fact, a huge quantity of electricity for lighting purposes. In fact, we are nearly using a quarter of the world total electricity production just for lighting purposes. Okay, that's a big problem from a global warming point of view. So now if you think about That's kind of similar to what Michel did in terms of moving across a long period of time. And if you think about material used for lighting, you can start basically around 1800 with a candle. And a candle, obviously, that's lovely, that's nice, but that's not necessarily extremely bright. And if the purpose is to use something for lighting, you're more interested in something that is extremely bright than just nice. So by 1900, the incandescent light bulb was invented, and you can still buy it in New Zealand. That's kind of, very practical, just plug in, and that's quite bright, so lovely. And we had to wait for another, basically, 100 years to have this kind of what we call energy efficient light or bulbs. They are called the compact fluorescent bulb. And when I'm talking about efficient or energy efficient lighting, what I want to say is that, well, you're looking at or you're trying to get bulbs that are extremely bright but doesn't use a lot of electricity. That's, in this sense, we have to think about energy efficient lighting, because that's what you want. And recently, for the last 4 or 5 years ago, you have commercially available what we call LED-based bulb, LED for light-emitting diode. And often my students say, oh, LED, what is that? And I say, but next time you go to Dick Smith or Harvey Norman, go to the TV area and you will see this 3D LED TV. 3-dimensional LED for light-emitting diode television. That's basically the function of these light-emitting diodes. They can also be used for in televisions. What is quite good here, and that's a demo I want to show you. I need my student Cameron. Where are you? Yes, here. He will show you all these different light-emitting diodes. You can touch them. You can look at them. They are kind of quite bright. And so what is fantastic with them, they are very cheap. We are just talking about 20, 30 cents each. Inside this box, you have just a battery, okay, a 9-volt battery. And the idea is basically to connect the material that is used in these light-emitting diodes to a battery. And by doing this, they will just emit light. And I want to show you that. That's what I have done in my lab. So at this point now, we are reaching a situation where we are looking at designing materials that can emit light. And you're interested in emitting different colors or wavelengths. Okay, so we need to find materials that can emit blue light, green light, and so on and so on. And here what I'm going to start in a couple of seconds, that's a material we can fabricate at the MacDiarmid Institute. We can fabricate this kind of materials. I will talk about them later on. But let's imagine I have fabricated this material in my lab. I take it, I go on the bench, I connect it to a battery. Oh. So I want to show you that that's my material. I have fabricated, designed it in my lab. I take it. You can see some electrical probes. I connect them to a power supply, so basically a large battery. You can see now I have my 2 electrical probes. That's basically 2 wires. I'm bringing these wires directly on the material I have fabricated in my lab. And what you see, that's fantastic. That's just light. These materials have basically the ability to emit light. I think it goes for a couple of seconds, different angles, and so on. And what you can see here, that's basically I've done a material that is able to emit blue light. I will talk about later on why we can change, or how we can change the color of these materials. The focus is not fantastic, but you can see that if you move across this material, you still continue to emit light. So that's kind of fascinating to be able to see this kind of light from a material on the bench. You can see with all the LEDs in front of you, if you look at them from an horizontal point of view, you can see right in the middle of the LED or the bulb, this small part of material that emit light. That's in fact just a piece of this material that has been taken and put right in the middle of these light-emitting diodes. Okay, that's finished, that's good. Now the question is, wow, can we get different colors? Yes. And the way we can get different colors is our ability to tune, once again, the size, the structure, the different atoms in the materials we are using. That's the way we are changing the color. Okay. I want to talk about that. I can see some senior people in the audience. That's great. When I'm talking about light-emitting diodes, Well, you may remember that already in the 60s or the 70s, we had the red LEDs, the yellow LEDs, and the green LEDs. Okay, it has been around for a long, long time. There is a missing one. It was the blue one. We didn't have the right material for the blue one. We didn't know the structure, we didn't know how to play with the structure, the atoms, the size, to be able to find a material that will be able to emit blue light. That's what it has been done by the end of the 90s by someone called Soji Nakamura, and he received the Nobel Prize a few years ago. What he did, okay, he was really good, he was a fantastic designer, I often call us chef because that's kind of like cooking, and he got all the ingredients, all the structure, the size in order to fabricate these blue light emitting diodes. And at this point, he knew he will become rich and famous. Because we already had the yellow light emitting diodes. And if you combine the yellow light and the blue light, you end up by having a white light. I mean, your eyes basically recognize the blue and the yellow lights as something white. So we have been able to develop these white light emitting diodes that are now used in most of the traditional lighting in your house. How we do that? Okay, I will say that's kind of combining many, many things. But the idea to get this blue LED or white LED is to combine 3 different metals: gallium, aluminum, and indium. And we do that also by combining them with a gas called nitrogen. And by having the right proportion of metals, or right size or structure, we will change the color of the light emitting diodes. We can get some purple, blue, or yellow, and so on and so on. So it's based on playing with material and size and structure again. I love it. That's just to show you. Now this is not just about finding a material by mining or at the beach or somewhere in the countryside that will be able to emit light. No, we have to design them. We have to create them. And to do that, well, you can imagine like us on the bench with all these different metals or atom or gas, how we can combine them, how we can assemble them in order to get the color we want. So that's what we call that material design now. And what is really important, that's to know the right recipe to get the color you want. Because if you go to a shop and you say, oh, I want a green light, but you end up by having a blue light, you may be a bit disappointed. So that's exactly what's going on when you're at home. You're ready to prepare a nice meal. What you have all the ingredients on your bench, they are in front of you. And obviously that's really important to choose the right ingredient at the beginning. Don't put the meat before the wine sauce, and so on and so on and so on. I would like just to say a couple of words about something that is kind of a little bit the opposite of light emitting diodes. That's what we call photovoltaic materials, also known as solar cell. And the idea here is basically to look at what will be the effect of the light on materials. Okay, so if you expose these materials, silicon, in fact, a good material, to the sun, the radiation from the sun, well, silicon will be able to convert the radiation or the sunshine into an electrical current that you can use now for different purposes. Okay, you can see silicon works kind of very well, it's kind of quite cheap, but you have some, as always, pros and cons. And one of the negative aspects, I will say, of silicon is the fact that it's very rigid. You can only basically buy them in a kind of flat and rigid array or panels. What we're kind of interested in the MacDiarmid Institute is to look at solar cells or photovoltaic materials that are more flexible, like made of plastic. So you can imagine like having your iPod in your arm and you put this flexible plastic photovoltaic material around your arm and you go for a run, and in fact the solar cell will basically provide some electrons and electricity to your smartphone. So that's kind of a possibility, and the type of materials and application we are interested in the MacDiarmid Institute.
So you can see that Frank only goes running on sunny days, I can tell that. And one of the great things about being a researcher is we get to not every so often come out into the public and speak about our research. So we've talked about photovoltaics and LEDs. Now let me tell you something. If you've ever taken a gecko and you've turned it upside down and you've thrown it at the ceiling, it'll stick. And if you pull it off and you do it again, it'll re-stick. And if you do it again, it will stick for as many times as you continue to throw it. Please don't tell Auckland Zoo this is what I do with their geckos. However, how on earth does a lizard that is so heavy, how is it able to stick all of its weight on just one toe? Nanotechnology. So gecko feet have tiny little nano hairs on the ends of them, and that's what makes them stick and unstick. Now that means never-ending sticky tape in my world, but it seems like something that I would want to try and invent. And so this stickiness that we learn from nature is what we call biomimetics. Bio for biology, mimetics for to mimic something. So basically we're copying biology. Now a lot of people think that researchers like me are smart. What we don't tell you is we're just copying what's already out there and pretending it's our own idea. So the gecko came up with this idea to have tiny nano hairs on its feet. And what we can do, and some of the things that I do in my research, is scan the foot of a gecko, understand the size of these tiny hairs on their feet, and then use something called a 3D printer to print them. So we can copy them. And what I have here are some examples, which I will pass around, of tiny little gecko head copies to make never-ending sticky tape. Now this one I have here isn't made out of a material that's sticky, because once you start to press on it you damage it, but it's one that can be passed around, you can touch it, you can sort of feel how it feels different in one direction or another. Just pass that around. So never-ending sticky tape is one of the things that I get to do in my lab. The other thing that I'm fascinated about, and my research has focused on recently, and something we do a lot at MacDiarmid Institute, is learning from nature and understanding why water rolls off surfaces or not. Again, biology has some great lessons to teach us. So if you've ever looked at a lotus leaf in a pond, or if you have a veggie garden, if you've ever seen your broccoli or your kale when it's raining, you'll know that the water runs right off and that it never gets wet. Now, this is a great experiment if you have kids. Go find some broccoli and some kale and do some drop experiments, and it's great to see the water ball up like this instead of lying flat in a puddle. Now, how does it do that? Well, I started looking at this is my iPhone video of a lotus leaf and how the water is balling up on it. And you can see the leaf isn't getting wet, and it's not because it's oily. It's because of this thing called biomimetics. If we put a lotus leaf under an electron microscope, again, looking at its surface using electrons, this is what it looks like. It's bumpy. It's got these tiny little nano bumps. Now, as a person who makes nano bumpy things, I thought, well, what if we just stick nano bumps onto things that we know? Will it do the same thing? Well, there's only one way to find that out, and that is using science. So I see there's two girls at the front. Do you think you can help me do something here? Can you just hold this tray? You hold one end, you hold the other end. What, does it look like a standard tray? Yes. It's not complicated. It doesn't look very odd. Now, I'm going to get you to watch this. I'm going to put some water onto this tray, and you tell me if I put it on this side or this side if it's different. Are you ready? Are you watching? Are you holding? Let's do this side first. Can you see a difference? What's the difference?
On this side it's balling up, and on this side it's just splattered.
Just splattered, balling up. I love that. That's very scientific. Okay, so what's happened here is these tiny little nanoparticles of silica or sand. I've put nanoparticles on half of the tray, and I've just left the tray without them on the other side, and you can see they're very different. Hey, and can you roll them around a little bit? So when you roll them around, the balls roll really, really quickly. Do you guys want to pass it around? If you want to look at the tray, you're very welcome to move the tray around. So, I mean, I spray this on all sorts of things at home, okay? But it's really useful for times when you don't want, like my clothing, for times when you don't want things. So in the medical industry, for example, when you have a lot of fluids that you don't want sticking to surfaces, you can coat this on to make them really easy to clean. Now, Cameron here is going to help me with a little experiment. Oh, you got a light. I'll swap your light for this. So you can use this not only to do scientific things, but as an educational tool to teach a concept that we call hydrophobicity. We'll get there. So hydro is water, phobic means afraid of. Now things can be super hydrophobic, means they're very afraid of water, so the water really balls up, or hydrophobic. The only difference is the angle that the water balls up at. So Cameron, I'm going to give you some sand. Can you tell me if that sand is wet or dry?
Dry.
Dry. How can you tell it's dry?
Because it's not in water.
Because it's not in water. Does your finger feel dry if you touch it? Okay. So do you want to pour it into this glass for me? Okay. It's still dry in there, yep?
Yes.
Right. What happens when you pour water on things?
They get wet.
They get wet. Everybody agreed? Science, yes, says they get wet. Okay, I'm going to pour some water onto here. So the assumption is that when you dig out the sand, it should be wet, yes? What happened?
It's dry.
It's dry. Are you sure? What about if you mix it really hard? Maybe it didn't mix enough. It's still dry. So the secret here is we have sand with nanoparticles of sand over each grain of sand, and those little bumps, just like in the lotus leaf, stop the water from wetting it. So Cameron, you're welcome to spill it around. Don't eat it. You can eat it. It's fine. It just means I don't have any to go home with. Cameron, do you want to help pass it around and show people how that works? So that is hydrophobic sand. It just has nanoparticles on things to make it stay dry. And you can dig it out, you can touch it, it's not toxic at all. The reason why we did it with sand is because we're using nanoparticles of sand to actually stop the water from sticking. And so it just shows you that you can do it in a really non-toxic way to start to create surfaces that never get wet, which is useful in some industries. The opposite of that is hydrophilic. There are times when you want to create surfaces that are very, very wet all the time, and so you can change what you do at the nanoscale of the surface to change how fluids interact with them. And so this is not, hold on, let's see if it goes back, is what it looks like at high speed. So here's a normal surface, but we've put nanoparticles or nanostructures on the top, and you see when you drop water on it, the water prefers to go somewhere else rather than stay and create a puddle. So these are super hydrophobic surfaces, and something that researchers at the MacDiarmid Institute spend a lot of time doing because we think it's really important to stop things from getting wet. I do a lot of research on ice-phobic surfaces. How do you stop ice from sticking to things without needing de-icer or chemicals? Now, we don't have much time, we only have an hour. We could go on all day about types of materials that there are, whether they're useful or not. I thought, seeing that you may be wondering why I have a blue pen today, that we would show you at least one slide on biomaterials. So you can make materials, lead, titanium, steel, but only some of them would you want to put in your body. Lead is not one of them, nor is mercury. So when you're thinking about metals that go inside your body, you have to make them biocompatible, meaning that your body doesn't reject them or react with them. We can also copy nature to make new materials such as soft materials, collagen, elastin, to replace you when you start to wear and tear. Now I wore and tore a little bit accidentally recently in that I managed to break my hand, and luckily materials, and these are titanium, this is the inside of my hand as of 2 weeks ago, are used to create screws and plates that can be screwed to put my hand back together, and slowly the bone will start to heal around it, hopefully, that's the plan, so that eventually my hand will start to work again. These are materials researchers that do just biology and biomaterials. So you can't put every material inside the body. So as we research materials, we don't just create titanium to go in there, but MacDiarmid researchers are making silver nanoparticles that attach to the titanium to make them antibacterial. Because one of the biggest problems when you put something inside your body is infection. And so when you close the bacteria in there, they start to grow and you get infection at the site. Infection in the bone is one of the worst complications you could ever want. So a lot of our researchers are looking at how do you make metals that go inside the body resistant to bacteria so you're much more likely as a patient to recover. And so we do lots of things in biomaterials. With soft materials, we have a researcher in Christchurch who's actually 3D printing collagen to try and make the collagen and the cartilage in between your knee joints that tend to wear very quickly. All of us who have old weary knees know that if you could find a material that you could put in there that was soft to cushion your knees again, that would be great because they don't repair themselves. Our cartilage is the only material that doesn't repair itself in the body that we seem to wear through before we get too old. And so we're actually creating 3D printers with that to be able to do that. Now we're not going to talk about soft materials or biomaterials. I just wanted to show you that the world of material science is huge. And what we're doing in New Zealand is just the tip of the iceberg based on all the new materials that are being invented as our world goes through this digital era, and as our materials start to wear before we're ready to go. And so we're going to have to start replacing our bits much more quickly. And so that is how here in New Zealand we do this. We take quality materials, some smart researchers, controlled manufacture, and we do a high value add. We're really incredible at exporting amazing nanomaterials and advanced materials, because it's not just what you have, it's what you do with it that matters. And so as materials engineers here in New Zealand, we at the MacDiarmid Institute are hopefully putting New Zealand on the map to create some really smart materials, and you never have to wash your windows again wherever that's gone. And so that is what we do at the MacDiarmid Institute, and that is how New Zealand is really unique. If you want to find out more about what we do, we've got researchers who commercialize some really interesting things. My favorite is Cather Simpson from the University of Auckland. She's an investigator, and she has just created a company called Engender. And what it does is it takes tiny little nanotubes, because she's found out that you can take the sperm of bulls and their different sexes. So if you're going to create a male or a female, you can tell by the sperm, and she creates these tiny tubes, and they only fit down one tube. So that then you can only create female calves, which is helping solve some of our bobby calf problems. We've got another group, Justin Hodgkiss from the University of Victoria, who's doing a separate startup called Aroma Bio, which is actually finding whether or not there are toxins in our water system. They get little nanoparticles to fix and change color, just like the stained glass. If there is, he's looking at estrogen in our water, because we know that we have a lot of effluent into our water, and actually those hormones are getting back into our water cycle. They can detect whether that's there or not. We get to hang out with a whole bunch of cool, nerdy researchers doing cool, nerdy things. That's what we do at the MacDiarmid Institute. We are all over the country, and so with that, that is our research. We are opening this up for questions, but thank you.